Hi, thanks for listening. I'm Sawala. I work at the University of Helsinki, and what I'm showing you today is done mostly in collaboration with Meriteria, who is a student in Helsinki, and also other collaborators in Helsinki, Durham, and Leiden. And all the plots I'll be showing you today from my own work are in two papers that are also on arXiv. One is already published, and there are many more plots in those papers that I won't go through today, but you can see more details in the papers. The topic is the giant arc, filament or figment. So the giant arc is a very large pattern in the universe, and large structures are nothing new. The giant arc certainly wasn't the first one. There's become the famous Sloan Great Wall, you can see here on the top, also the CFA stickman. And then in the bottom you see analogues in the Millennium simulation. The plot is from Spring et al. 2005. And you can see that the Millennium simulation and other simulations that assume ΛCDM basically readily produce large-scale structures that extend to maybe a few 100 megaparsecs. Now the giant arc is claimed to be even bigger. It is claimed to extend to about a co-moving gigaparsec, and that the discoveries say appears to be in tension with the large-scale homogeneity that underpins the ΛCDM model. It's also claimed to be quite overdense, and that also would be an extreme outlier in the ΛCDM universe. The giant arc, which you can see here in the middle, was first discovered by I and then confirmed as a friend-to-friend group. It contains basically 44 magnesium-2 observers. Magnesium-2 observers you can see here as gray circles, and in the background in blue you see the quasars in the same field of view. This figure is from Lopez et al. 2023 that described the discovery of the giant arc. Now, magnesium-2 observers are basically a sample of foreground galaxies. So you have foreground galaxies, and they become magnesium-2 observers if they appear along the line of sight to a background quasar. And if the background quasars are uniformly distributed, then the magnesium-2 observers are basically a sparse random sample of the foreground galaxies. So should we care? Well, this is cosmology from home. So as cosmologists, I think we should care about patterns like the giant arc, and especially claims that it contradicts our standard cosmological model. And indeed, the giant arc receives many citations, often from people who propose alternatives to the standard cosmological model, where large-scale anisotropies and inhomogeneities would basically be a feature of the model, and the giant arc would be a manifestation of such features. And also the giant arc is often discussed in popular discussions about cosmology. Also has its own Wikipedia article. So I think also as cosmologists we should care whether this is a real phenomenon and what the origin of the possible tension with ΛCDM is. There are a few peculiarities about its discovery. So as I mentioned, it was first seen by I, and then described as a friend-to-friend group. So the friend-to-friend algorithm basically groups points together that are separated by less than one linking length. And so the linking length is an important parameter of the friend-to-friend algorithm. And in the detection of the giant arc, basically the authors varied the linking length so that the giant arc would appear most clearly, and they settled on a linking length of 95 co-moving megaparsecs. And then also from a very large sample of magnesium-2 observers, they then considered a thin redshift slice, and they chose the redshift interval so that the giant arc, which I mentioned they had already seen by I, would basically be identified in the most clear fashion. So they ended up with a slice that's about 1.5 by 1.5 co-moving gigaparsecs on the side, and it's only 338 co-moving megaparsecs deep. Now, that's important because this is only a small multiple of the linking length, and in fact, most of the volume in that slice is separated by less than one linking length from the side, and also a structure as big as the giant arc basically becomes a 2D structure within such a slice. So even though the analysis is formally done in 3D, it's kind of looking at a slice that is so thin that it becomes almost a two-dimensional analysis. And any structure that is as big as a giant arc that would fit in such a thin slice is by definition already highly anisotropic. But we wanted to ask, how rare is it? And so for that we needed a big cosmological simulation. It wouldn't fit in the box of the Millennium simulation, for example. So we used Flamingo 10K, which is a large simulation assuming ΛCDM cosmology. It spans 2.8 co-moving gigaparsecs along one side and is resolved with 10,000 cubed particles, so it's also a very high resolution simulation that allows us to resolve all the halos that could potentially be magnesium-2 absorbers. And we consider the output at refute 0.7 for most of the plots that I'll show today. And that's because there we have the full particle information, which we will also use. But in the paper we also discuss basically the structures that we find at other redshifts and also on different scales. And then we draw from this sample of halos samples of equal point density and slice geometry as was used for the giant arc. And then we can also measure the underlying matter density using the simulation particles. And also we consider just random shot noise samples, so uniform random samples with the same density and in slices of the same geometry. And we analyze those with a friend-to-friend algorithm, those samples of halos, or points in case of the random samples, with the same Lincoln length of 95 megaparsec. And for each friend-to-friend group that we find, we basically classify it according to its length or its extent, which we define as the maximum pairwise distance between points. And then the anisotropy, so for that we use the common definition of the ratio between the square roots of the eigenvalues of the covariance matrix. The smallest of the eigenvalues, which we call C, is always small just because of the thinness of the slice, but we basically compare the ratio between the middle and the largest eigenvalue. And if that ratio is small, then the structure would be filamentary. If that ratio is large, then the structure would be more like a sheet. So we're looking for small ratios of those eigenvalues, which would be filaments that look like the giant arc. And then we measure the convex hull overdensity. So we draw a convex hull around every friend-to-friend group and measure the density of points within that and compare that to the average density of points in the slice. This is exactly how it was done in Lopez et al. And then we also measure within the same convex hulls the matter overdensity. So what do we find? Well, we find actually many patterns like the giant arc in the simulation. So this is just from one random sampling of the simulation, the first random sampling. In the middle you see the giant arc itself. Each panel here is 1.6 by 1.6 co-moving gigaparsecs in size. And then around it are 8 analogs in the simulation. You'll notice that the length of the giant arc wasn't clear to us. We couldn't get the data, so we basically just estimated it, but we only saw it in projection, so that's why there's a range of sizes. In fact, the giant arc is a little bit shorter than what we had estimated, but I'll come to that later. But then here you see basically analogs that are very similar to the giant arc. None is exactly the giant arc, but we find many giant arc-like patterns in the simulation. Now the question is, are there real structures? So if there are real structures, if they reflect some underlying overdensity, then you would expect that if you take a different random sample, a different sparse sample from the same simulation region, you would find more or less the same structure, of course slightly different, but basically if you find one long giant arc-like feature in one place in the simulation, you draw a different random sample of halos. If this reflected some underlying overdensity of galaxies there, or halos, you'd expect to find a similar pattern in a similar position. Whereas if you go to a different slice, a completely different region of the simulation, of course you'd expect to find completely different structures. However, if these are just random patterns, then basically changing between different slices wouldn't matter. It's just every time you draw a new random sample, you get something completely different. And this is actually what we find. So what this shows is the cumulative distribution function of the length of the longest anisotropic pattern, so the longest giant arc analog we find in a given sample of a given slice. And these different thin red lines that you basically can't tell apart here are all the different slices of the simulation. And then the distribution function is drawn from drawing random samples repeatedly from the same slice. And so basically in every slice, in some random sample, you'll find nothing longer than 400 megaparsec. But also in every slice, in some random sample, you find something as long as a gigaparsec. And you find structures as long as the giant arc. Again, we didn't know its full extent, or its precise extent, in between 20 to 10% of cases. So the giant arc is really nothing unusual, and also at least in the simulation, it does not represent any real structure. We can also look at the overdensity. So in red is the histogram of overdensities of comparable structures measured in the simulation, and in gray is the same, but for comparable structures found in these random short noise samples. And we see there's basically very little difference between the patterns we see in the simulation and the patterns we find in fully random distributions. But also the overdensities we measure, you note that for the giant arc the overdensity was 0.9. 0.9 is not a 4.5 sigma outlier, it's in fact right in the middle of the distribution that you'd get for just random patterns basically as we find them in the simulation. And this is just a feature of the algorithm. So if you draw a convex hull around an existing friend-to-friend group, you'll find that that friend-to-friend group appears to be overdense. This is not a surprise. However, when we then look at the matter density within those same convex hulls, they're not very overdense. They're just very slightly overdense, but you might even find some that that are underdense, and that's because these are not really real structures in the simulation. So if we found a matter density of 0.9 or matter overdensity of 0.9, that would indeed be in tension with ΛCDM on these scales, but that's just not what we find in the simulation. Now to conclude, the giant arc, or patterns like the giant arc, are completely expected features of the statistically homogeneous universe, and it's important to stress that statistically homogeneous does not mean that you cannot find a sparse sample that looks inhomogeneous. And specifically, the giant arc is completely consistent with ΛCDM. Now, you will note that I still have a few minutes left, and I'm not yet at the end of the talk. So there was a rebuttal to our paper by Lopez and Klaus, whom we had provided our simulation data. And so they claim to have performed an enhanced analysis and find that gigaparsec patterns are nowhere to be found in ΛCDM. So they look at the same data and they come to completely different conclusions. Why? Well, they basically claim that we should have used a different linking length. So we used the same linking length that they had used for the observational data, but they say that in the synthetic data we should have used a much smaller linking length because our synthetic data did not include an inhomogeneous background of quasars and also did not include redshift errors. So I won't have time to go through the arguments in detail, but they say that we should start with a linking length of 65 megaparsecs, and then the inhomogeneity of the quasar background would increase this linking length by about 20 megaparsecs. So what they do is they basically measure the density of quasars in apertures of 65 megaparsecs squared, find the mean is 15.6 and the standard deviation is 5.7. And then they say, okay, a 1.5 sigma should be considered as underdense. Then they compute the ratio between the mean and the difference between the mean and 1.5 sigma, that's 2.23. And then they multiply the linking length by 2.23 to the 1/3 to get to 85.2. Now, it's important to note that even a homogeneous quasar background, when you measure the count within a small aperture where the mean is 15.6, would have a standard deviation of about 4. And also this threshold of 1.5 sigma is quite arbitrary. One could have used a threshold of 1 sigma or 2 sigma and basically obtained a different correction. Why the correction should be at 1.5 sigma is not explained, but with this correction they get to 85.2 megaparsecs. And then they say that because of the redshift errors, they amount to about 7 megaparsecs uncertainty in the distance. They round this to 9. They add the two corrections together just linearly, and then they arrive at 95 megaparsec, which is the link length that they used for the observational data, but they said we should use 65 megaparsec instead when looking at the simulations. So they reanalyze our simulation data with 65 megaparsecs and get this distribution of lengths, or the length of the longest structure in a slice. Find very short structures. The giant arc is much longer. Actually, it's not as long as we had thought. It's only 740 megaparsecs with our definition. We didn't know this when we wrote our paper, but basically structure of 740 megaparsecs are just slightly more common than structures of 770 megaparsecs. But certainly, when you use a much smaller linking length in the simulation, you don't find structures as long as the giant arc if you use a longer link length for finding those. Now the question is, should you use a different link length? And I would argue that not. So I already mentioned that there were a few quite arbitrary choices getting to that longer linking length. But maybe more importantly, we had assumed a uniform quasar background, and they argue that we overestimated the abundance of such patterns. I would say that's not at all obvious, and I will also show in a minute that indeed it is not true. And also, when we consider uniform random samples, then adding small random errors to those does not actually change the PDF at all. In fact, it's easy to prove that you get a different random sample every time, of course, when you add small errors. But if the initial assumption was a uniform random sample, adding small errors gives you new uniform random samples with the exact same PDF. But we can argue about this, or we can also just demonstrate it explicitly. So what we did is create new random samples with an inhomogeneous quasar background. Then we also add these small errors, even though that has no effect, but just for completeness. And then we select samples just as we had done before with the same number density and slice geometry. So this shows our different quasar backgrounds, uniform and then increasingly inhomogeneous with a different covariance length. And we measure with the same metric, basically the standard deviation in cells of the same size. At a covariance length of 100 comoving megaparsecs, we get the same standard deviation they have measured. Now the question is, would you expect to find more or less patterns in the foreground if you make the background inhomogeneous? Well, you might already guess that the answer is you will find more, and this is exactly what we found. So this shows the PDF of the longest structure in a given slice. This is the cumulative distribution function. This is now the actual length of the giant arc, which is shorter than we had initially estimated. And you can see the dark blue line here. This is assuming the uniform quasar background gives you a pattern like the giant arc in about 21% of cases. If you make the quasar background inhomogeneous, you actually get more patterns in the foreground. Not by much, but it's definitely not less. So maybe some additional conclusions. It's really dangerous to adjust parameters for no good reason between the analysis you do to detect a pattern and then the null hypothesis test. So I think this is really crucial, and then to claim a high statistical significance, of course, becomes somewhat meaningless if you're not comparing apples to apples. And maybe to the community, I would say be skeptical about claims of detections of inhomogeneities. That doesn't just apply to this one, particularly if simple tests like the ones that we have conducted are missing. Thank you very much for your attention, and I hope to see you all during the discussion time.